This is 4.3.5 Mixing Problem, Applications of Linear Equations. When we are talking about mixing problem, it means that you are given a tank. Inside the tank, you have some solutions of prime, and you will have some solutions that is entering the tank. And let's just assume that the solution is entering the tank with some rate, and let's just call the rate as the input flow. And the concentrations of this solution, we will call it as input concentrations. Then the solutions that is entering the tank will mix with the solutions in the tank. Then the liquid will leave the tank at some rate, and let's just call the rate of leaving as the output flow. And the concentrations of this liquid or the solutions, we will call it as output concentrations. In mixing problems, there are things that you can control. Okay, the first thing that you can control is the input flow. Okay, because you can determine how fast the solution is entering the tank, and you also can determine how fast the solution is flow out from the tank. Okay, the output flow is another thing that you can control. Input concentration will be another thing that you can control, but you cannot control the output concentrations. Okay, because the output concentration is the result of mixing. Okay, it will change according to time. Okay, when you multiply the input flow with the input concentrations, then you will get something called input rate. And if you multiply the output flow with the output concentrations, and you will get something called output rate. Okay, let's just assume that the Vt as the volume of solutions in the tank at any time t, and the At equal to the amount of substance. Okay, the substance could be the salt of the sugars in the tank at any time t. Then the rate of the change of the substance, okay, that is the dA dt, will be equal to the input rate minus the output rate. And later you will come across three cases. Okay, the first case is that you will have the input flow equal to the output flow. And the second case will be the input flow greater than the output flow. And the third case will be the input flow less than the output flow. Okay, let's just look at this example. So let's just let the Vt equal to the volume of prime in the tank at any time t, and At equal to the amount of salt in the tank at any time t. Okay, let's just begin to extract the information from this example. Okay, first of all, it says that a tank is filled with 15 liters of prime. Okay, so this 15 liters of prime is your initial volume of the prime. Okay, so this is actually your V at time equal to 0. Okay, so your V0 is equal to 15 liters of prime, in which is dissolved 5 grams of salt. Okay, so this 5 grams of salt is the initial amount of the salt in the tank, so that is your A0. So your A0 is equals to 5 grams. Okay, and then let's just construct a table. So now let's just begin to fill in the blank, okay, for the table. Okay, so then let's look at this one. It says that, okay, the brine containing 4 grams per liter. So this 4 grams per liter is basically your input concentrations. Okay, so your input concentration, that is 4 grams per liter. Then fill in the blank in here. You have 4 grams per liter, and it enters the tanks at 2 liters per minute. So this is actually your input flow. So you have an input flow of 2 liters per minute. So you have 2 liters per minute. So then we fill in the blank in here. So we have 2 liters per minute. Okay, and then it says that the mixtures leave at the same rate. So it leave at the same rate. That means that it's leave at 2 liters per minute. So you have the output flow that is 2 liters per minute. So if you look at this case, basically we have a case of the input flow equals to the output. Okay, so we have the case of the input flow equals to the output flow, because you have the same value here. So imagine that you have a tank. Okay, so the tanks, okay, you have the solutions that is entering at 2 liter per minute, and it's also leaving at 2 liter per minute. Okay, what happens to the volume of the solution in the tank? Okay, so the volume of the solution in the tank will be constant. Okay, the solution that is in the tank will be constant, it will not change because the input flow is equal to the output flow. Okay, what happened if initially you have 15 liter of brine, and if the solution is constant, it means that okay, your VT will be also the same. Okay, so initially it's 15 because the input is equal to the output flow. Then as the time goes on, the volume of the solutions in the tank will also be 15. Okay, because it will not change. So instead you will have your VT here, that is 15. Okay, of course, you also can use your formula to gain the value of VT. So the formula that we can use is actually this one, that is your V0 plus input flow minus output flow multiplied with the time. So your V0 here is 15, and your input flow is 2, and your output flow is also 2. So you have 2 minus with 2. Multiply with the time. Okay, so 2 minus 2 will give you 0. 0 multiplied with t, you have 0. So 0 plus 15 will give you 15. So then we have Vt is 15. Okay, so now, okay, once we have identified our Vt, the next thing that you have to figure out is the output concentrations. How are we going to know our output concentrations? Okay, our output concentrations that is we're going to identify through the formula. So the formula for output concentration will be AT divided by VT. But actually, we do not know what is our A at this time. So let's just put A only. But for the VT, we know that the VT is actually 15. So that's why we have A divided by 15. So this is actually your output concentration, and this output concentration will use the same unit as the input concentration, that is the gram over liter. So we have gram over liter here. So let's just fill in the blank in here. Okay, now the next thing that you have to do is you have to identify what is your input rate and your output rate. Okay, how we're going to know our input rate and output rate? So that is through multiply. So you can multiply your 2 with 4. So you have 8. Okay, and then okay, if you look at the unit and input flow, you have liter per minute, and input concentration you have gram per liter. So actually the liter here you can cancel. So then you can see that I have the unit of gram per minute. Okay, so your input rate will be 8 gram per minute. Okay, so same thing happened for the output rate. So you multiply 2 with A over 15. So you have 2A divided by 15. Okay, and same thing happened for the unit. So the liter here you can cancel. Okay, so you can cancel the liter here and the liter here. So you have the unit of gram per minute. So okay, and the 2 over 15, okay, is a fractions you can put aside, and you put the A next to the fractions. Then you have this one. So that's why we write it as this way. We have 2 over 50 A gram per minute. Okay, so then let's just identify the questions for this example. The first question says that okay, you have to figure out the amount of salt in the tank at any time t. So basically, it's asked you to find the AT, the mathematical equations for the AT. Okay, for the question B, how much the salt is present when the t approaches infinity? Okay, so this one mathematically you can write in terms of this way. So you can write this is the limit, the time approach to infinity, and what is the amount of the salt? Okay, this is a question mark. Then we have this one. Alright, so okay, let's just go to figure out how to solve this example. Okay, now solve this problem by using its differential equations. So that is dA dt equal to input rate minus the output rate. So your input rate, that is dA. Okay, so you have dA dt equal to the 8 minus with the output rate that is 2 over 15a. Okay, rearrange this one, then you have the next line. Okay, once we have the differential equation for the mixing problem, so we don't need this table anymore, and we don't need the initial volume anymore. Okay, let's just compare the differential equations that we have here with the general form of the linear equations, that is this one. So if you look at the linear equations, you have the dy dt plus pxy equal to qx. Okay, so means that you have the variable x and y in the linear equations. Let's just compare this one with our differential equations for the lectures problem. Okay, so you have the variable a and variable t here. So let's just compare the positions. So if you compare the positions for the linear equations, so for the linear equations, the positions of y, okay, is took over. The position of y is took over by the variable a, okay, in the mixing problem, and the variable x, the place of the variable x is took over by the variable t, okay. Okay, so that is for our differential equations for the mixing problem. Okay, if you recall back in our linear equations, okay, the next thing that you're supposed to do is you have to find the integrating factor, that is your if equal to e to the power px dx. It's just that in the mixing problem, the x here, so you have to change to the t. So then we have the next line. And once we have identified the integrating factor, the next thing that you have to do is you have to solve the differential equations by using this formula. Okay, so we have to modify this one, okay, just that we can use in the mixing problem. Okay, so your y here, so you have to change to the a, okay, and the x here, so we have to change to the t here, okay. So then we have the next line. So this is the three equations we're going to use it for solve this example. So okay, so once we have identified the differential equations, the form of differential equations for the mixing problem, so let's just identify what is the PT and the QT. So your PT here is the one that is next to the variable A. So this is your PT, so your PT is 2 over 15, and your QT is equals to the A. Okay, and then the next thing that you're supposed to do is you have to find the integrating factor if equal to e to the power pt. Okay, so now you know what is your pt. Your pt is actually 2 over 15, so you just substitute it. So integrate it, and you have your value of the you have the e to the power 2 over 15t. So that is your integrating factors. Okay, so once we have identified the integrating factors, let's solve it. So by using this formula, so then this is what we have here. Okay, so substitute your IF into this formula. So your IF is the exponent. Okay, and then your QT is 8. And then you have the IF. Okay, and then integrate the right hand side. So once you have integrated the right hand side, this is what we have here. Okay, simplify it. Okay, so and then this is what we have. Okay, so then divide all of the terms that you see here with the exponent. So then we will have this one. So let's just name it as equation number 1. And the next thing that you have to do is you have to figure out the value of c here. So your value of c here, then you can get it from these informations. As a0 equal to 5. So substitute a0 equal to 5 into your equation number 1. So your amount of the stock now is actually 5. Okay. And your time here is actually 0. So you substitute, then you have the next line. Okay, you simplify, then you have your value of c. So so your c is actually negative 55. So substitute c equal to negative 55 into your equation number 1. Then you have the next line. So let's just name it as equation number 2. So your equation number 2 is basically the answer for this question A. That is the mathematical equations for finding the amount of salt in the tank at any time t. Okay. Now let's just go to the second questions. Okay, find the limit when the time approaches to infinity. So, okay, what you have to do is you just have to take the equations number 2. Okay, so like equal to equation number 2, just the time here. So you have to change to the infinity. So you have negative 2 over 15 multiplied with infinity, it will give you negative infinity. And e to the power of negative infinity is actually 0. So 55 multiplied with 0 will give you 0. So 60 minus with 0 will give you 60. So this is actually means that when the time approaches to infinity, the amount of the salt in the tank is 60 grams. Okay, let's just look at the second example. So again, we're going to assume that your Vt equal to the volume of the brine in the tank at any time t. Okay, the At equal to the amount of salt in the tank at any time t. And let's just extract the information from the example 2. Okay, first of all, it says that the tank has the capacity of 150 liter. So that is the first information that we could gather from this information. So tank capacity 150 liter. And then it says that it's filled with 10 liter of brine. So this 10 liter of brine is actually your volume at time equal to 0. That is your V0 is actually 10 liter. So your V0 is 10 liter. And then which is dissolved 30 gram of salt. Okay, this is actually your initial amount. So that is your A0. So your A0 is 30 gram. And then let's just construct a table. So it says that the brine containing 2 gram per liter. Okay, this is actually your input concentration. So you have a input concentrations of the 2 gram per liter. Okay, so you have input concentration that is 2 gram per liter, fill in the blank in here. And then enters the tanks at 4 liter per minute. Okay, this 4 liter per minute is referred to your input flow. So you have input flow that is 4 liter per minute. So let's just fill in the blank in here. And the mixtures leave at 2 liter per minute. So 2 liter per minute, that is your output flow. So your output flow, that is 2 liter per minute. So let's just fill in the blank in here. So you have output flow 2 liter per minute. Okay, now let's just look at the case that we have here. Okay, so now what you have here is you have the input flow. Okay, your input flow that is 4 liter per minute. Okay, that is greater than 2 liter per minute. Okay, you have a case of input flow greater than output flow, right? Because 4 is greater than 2. Okay, so when you have case of input flow greater than output flow, what happened to the volume of solution? Okay, now imagine that this tank is in front of you. Okay, so this tank is in front of you. Okay, and then you have the liquid or the solutions that is entering the tank at 4 liter per minute. Okay, at 4 liter per minute. And the solutions is leaving the tank at 2 liter per minute. Okay, what happened to the volume of the solution in the tank? Okay, the volume of the solution in the tank basically will increase. Okay, basically the volume of the solution will increase. Okay, if the volume of the solution is increased, okay, so what will be the Vt? So what will be the Vt here? So the Vt here actually you can obtain by using the formula. So the formula is this one. Okay, so means that you're going to use the Vt equal to V0. So your V0 here is 10 liter of brine, 10 liter of brine, plus with input flow. So your input flow is 4 liter per minute. So you have 4 minus with output flow. So the output flow is 2. So minus with 2. Multiply with time. So multiply with time. So 4 minus 2 will give you 2. So 2 multiply with t. So you have 2t. So your Vt is 10 plus 2t. Okay, once you have obtained your Vt is 10 plus 2t, the next thing that you have to figure out is the output concentration here. So your output concentrations that you can obtain by using this formula, that is At divided by Vt. So, but actually we do not know our At. So how are we going to, okay, we actually do not know our At. So what you have to do is you're going to put A only. But the Vt actually we know the Vt is actually 10 plus 2t. Okay, so the unit here, we're going to use the same unit as the input concentration. So then we have the answer for the output concentration. So this is the answer for the output concentration. Okay, the next thing that you have to figure out is the input rate. So how to figure out the input rate? That is very simple. So it's through multiplication. So we just multiply the 4 with 2. So we have 8. And the unit here you can cancel. So I will have gram per minute. So your input rate will be 8 gram per minute. Now, let's just figure out the output rate. So the output rate, we're going to multiply the 2 here with this one. So basically, you have 2 multiplied with A. Okay, then you have 10 plus 2t. Okay, and then at the denominator, basically, you can factor out 2. So if you factor out the 2, so I will have 5 plus 2, I will have 5 plus t. Okay, cancel out the 2 here. So you will have A 5 plus t. Okay, the A you can put it aside. So we have fractions. Okay, 1 over 5 plus t. Okay, the A we put it aside the fractions. Okay, the unit going to have the little cancel. So then we have gram per minute. So your output rate will be 1 over 5 plus t, A gram per minute. Okay, let's just look at the questions for let's just look question for this example. The questions for this example is they ask us to find the amount of salt in the tank if the tank has reached its full capacity. That is actually asking for the AT when the tank has reached its full capacity. Okay, once we have obtained all the informations, okay, let's just look at how to solve this example. Now let's solve this example by using its differential equations. Okay, so you will have your dA dt equal to the input rate, that is 8, minus with the output rate, that is this one. Okay, then this is what we have here. Okay, and then rearrange this one, we're going to have the next slide. So this is actually the differential equations for the mixing problem. Okay, so once we have obtained the differential equations for the mixing problem, we do not need the table anymore, and we also do not need the V0. Okay, then let's just compare the differential equations that we have here with the general form. Okay, so you can know your PT. So your PT is the one that is next to the A. Okay, and then you're going to know your QT. Okay, so your QT is 8. Okay, then let's just find the integrating factor, that is IF, okay, equal to e to the power of integrations PT dt. So your PT here is 1 over 5 plus t. So integrate this one, and will give you ln. Okay, so and then the e and ln you can cancel. Then we have your integrating factor is 5 plus t. Okay, and solve this differential equation by using its formula. So this is a formula. So let's just have, okay, this is actually A, and multiply with your IF. Your IF is 5 plus t. Okay, equals to QT. So your QT is 8. Okay, multiply with IF, that is 5 plus t. And this is what we have here. Okay, so expand the right hand side. Okay, and then integrate the right hand side. And you have 8 divided by 2. So 8 divided by 2 will give you 4. And then, okay, bring this 5 plus t to the right hand side. Then you have this one. Okay, and then name it as the equation number 1. Okay, let's just pick up the value of c here. So that is through these informations, you're going to substitute your a0 equal to 30 into your equation number 1. Okay, so it means that your a is actually 30. So substitute this one as 30 and substitute your time as 0. So just substitute into here. Okay, then this is what we have for the next line. Okay, then simplify the right hand side. You will get your value of c, that is 150. So substitute your c as 150 into your equation number 1, that is this one. Okay, then we're going to have this one. So this is actually your equation. Let's just name it as equation number 2. And this is actually the equations, okay, or the mathematical equations for finding the amount of salt in the tank at any time t. Okay. So then let's just look at the questions here. So the questions, okay, ask us to figure out the AT when the tank has reached its full capacity. Okay, so what is the tank capacity? So the tank capacity is 150 liter. Okay, recall back the formula that we have just now. That is the formula of Vt. Okay, and we have Vt equal to 10 plus 2t. So this Vt is actually the volume of the solution in the tank. Okay, at any time t. But how are we going to know the time for the solutions to reach the tank full capacity? Okay, so that is you just have to let this 10 plus 2t equal to the tank capacity. If you solve this equation, So you're going to get your value of t. So this value of t is actually means that at time equal to 70, the tank will reach its full capacity. So this is actually the time. But the things that we are interested to know is actually the amount of salt. So how are we going to know the amount of salt in the tank? So that is through substitution. So you're going to substitute your time equal to 70 into your equation number 2. So substitute the t here equal to 70. Then we have this one. Okay, then simplify it. Okay, that is the value of A. It means that when the time equal to 70 minutes, the tank has reached its full capacity and the amount of salt in the tank is 300.6667 grams. Now we have the third example. So let the VT equal to volume of the brine in the tank at any time t, AT equal to amount of salt in the tank at any time t. Okay, let's just extract the information from this example. This is that the tank initially has 50 liters of pure water. So this 50 liters is actually your initial volume of the solution. That is your V0. Okay, and of pure water, it means that pure water means that initially you do not have salt in the solution. Then you do not have the salt in the solutions means that your amount of salt at time equal to 0 is actually equal to 0. So you have A0 equal to 0 gram of salt. This is actually for the pure water. Okay, and then let's just construct the table. So it says that a solution with 2 grams per liter of salt. Okay, so the 2 grams per liter of salt is actually referred to your input concentrations. Okay, so input concentration you have 2 grams per liter. Okay, so let's just fill in the blank in here. Okay, and then it's added into the tank at 2 liters per minute. So this 2 liters per minute is actually your input flow. So your input flow is 2 liters per minute. 2 liters per minute. So just fill in the blank in here. Okay, and then the mixtures leave the tank at the rate of 3 liters per minute. So this is actually your output flow. So you have output flow that is 3 liters per minute. Then fill in the blank in here. Okay, and now, let's just look at the case that we have here. So you have the input flow that is 2 liters. That is less than the output flow. Okay, 2 is less than 3. So you have a case of input flow less than the output flow. Okay, what happened? You have a case of input flow less than the output flow. Okay, so now you have the solutions that is entering at 2 liters per minute and is leaving at 3 liters per minute. Okay, what happened to the volume of the solution in the tank? The volume of the solution in the tank will decrease. Okay, so when the volume of the solution in the tank will decrease, okay, what happened to the VT? So the VT, we're going to get it from using this formula. Okay, so this is basically means that you can obtain your VT by using this formula. So your V0 is actually equal to 50 liter, and your input flow that is 2, and minus with your output flow that is 3, and multiply with the time. Then you will have your VT. Okay, then the next thing that you have to figure out is the output concentration. So you're gonna get your output concentration by using this formula. That is AT divided by VT. So you do not know your AT, just leave it as A. But you know your VT. Your VT is 50 minus T. Okay, and this is basically your output concentrations. You're going to use the same unit as the input concentration. So let's just fill in the blank in here. Okay, then what is our input rate? So our input rate, you just have to multiply the 2 with the 2 here. So we have 4, and the unit will be gram per minute. Okay, so for the output concentration, just for the output rate, you just have to multiply this one with this one. So you have 3 over 50 minus T multiplied with A. So this is your output rate. Okay. Now let's just look at the question. The question asks us to figure out the amount of the salt in the solution at any time t. That is actually asked us to find the AT. So now let's just solve this example. Now let's just solve this example by using its differential equation. So you have your dA dt equal to the input rate. So input rate is 4 minus with the output rate. So your output rate is, this is the 1. So then we have this one. Okay, rearrange this one and we have the next line. So this is basically the differential equations for the mixing problem. So once we have obtained the mixing problem differential equations, we do not need the table anymore, and we also do not need the V0 anymore. Okay, let's just compare the differential equations that we have here with our general form. So you can know your PT. So your PT is the one that is next to the variable A. Okay, and then you will know your QT. Okay, and then let's just figure out the integrating factor by using this formula. Okay, substitute your PT into here, so you will have the next line. Okay, we're going to integrate this one. Okay, if you want to integrate this one, so you have to extract out the 3 here. Okay, so then you have 1 over 50 minus t dt. So if you integrate 1 over 50 minus t, that is give you ln. So then we have the next line. Okay, and you can bring this minus 3 to become the index. So we have the e ln 50 minus t to the power of minus 3. Okay, and the e and the ln you can cancel. Then we have the next line. Okay, then we're going to solve these differential equations by using its formula. So this is the one. So okay, let's just substitute what is our IF here. Okay, so we have A multiplied with the IF. So your IF is this one. And then equal to the integration QT. So your QT is actually 4. Okay, and then you have multiply with your IF. Okay, so we have IF here. Okay, so to integrate the right hand side, so what you have to do is you have to use the technique of substitution. So just substitute 50, okay, substitute u equal to 50 minus t. Okay, and then you differentiate both sided, and this is what we have here. Okay, and then you can bring this minus to the left hand side. You have minus du equal to dt. Okay, now we're going to do the substitution into here. So for the right hand side, you still have the integration 4. Okay, it's just this one. 50 minus t, replace it with u. So you have the variable u inside the bracket to the power of minus 3. Okay, the dt here, you can change to minus du. Okay, simplify this one. And this is what we have here. Okay, integrate this one with respect to the u. And this is what we have here. So simplify this one again. Okay, and this is the answer for the right hand side, but do not leave your answer in this way because it's supposed to be in terms of t only. So change the u back. So the u is 50 minus t. So change it back. That is what we have here. Okay, now divide all the terms that you see here with this 50 minus t to the power of negative 3. Then we have here. Okay, and then we need to simplify for the right hand side. Okay, so if you observe here, we have 50 minus t here. So let's just simplify it. So the 50 minus t, okay, you have a minus 2 here. So we have a minus 2. Okay, minus with the minus 3. So you have minus with t minus 3. So if you simplify this one, it's basically if you 50 minus t to the power of 1. Okay. Okay, for the right hand side, you have the minus 3 here. So this is minus 3 will give you a positive 3. Alright, so that is what we have for the right hand side. So let's just name it as the equation number 1. Okay, we need to figure out the value of the c for the equation number 1. So how are we going to figure out the value of c for the equation number 1? That is through this information. So we're going to substitute a0 equal to 0 into your equation number 1. So means that your a is 0, your time is actually 0. So simplify, then you can get your value of c. So this is your value of c. Okay, now substitute your value of c into your equation number 1. So substitute into here. So you have your value of c. Okay, that is 1 over 1250. So then we obtain the equations A. Okay, so this is actually the mathematical equations for finding the amount of salt remaining in the solution at any time t.